not spelled right, but.
That's right.
All right. Momentum is conserved. Collision, just a two-body system, nothing else involved here. And so it's a closed system, momentum is conserved. All right. So what's the formula for momentum?
Mass times velocity.
All right. Up here. So what's the total initial momentum? Oh, this is. Units?
Kilogram meter per second.
That works. Plus 0 from that one, kilogram meters per second. So my total, 144 kilograms meters per second. What's the total final momentum?
Same thing.
I hope so. Although I have asked that on tests before and been surprised that not everyone getting it. Well, since they stick together, so afterwards their mass is 8 kilograms times whatever the final velocity is. And so from that, the final velocity is,
18 meters per second.
all right, simple conservation of momentum, perfectly inelastic collision problem. Or some textbooks would call it completely inelastic, and other textbooks would call it inelastic. Now, I'm going to shift reference frames, because otherwise it wouldn't really connect. As I shift reference frames, I'm going to shift to the zero momentum frame. In other words, so you're just sitting here watching this thing go by 48 meters per second, so 100 and something miles an hour, crashes into the next one, and then they both start moving. In the moving frame, I'm going to move along so that afterwards it's not at rest relative to me. In other words, I'm going to be traveling at 18 meters per second. That would be the zero momentum frame. So I'm going to shift, so you can call this the S frame and the S prime frame. And the S prime frame is going to be traveling at 18 meters per second. This is all classical physics here. We don't have to worry about any time dilation or length contraction. So my 3 kilogram mass there, how fast is it going in the new frame?
About 30 meters per second.
Yep, just subtract it. So this is going 30 meters per second. That's the 3 kilogram. And how fast is the 5 kilogram mass going?
Negative 18.
So we look at the momentum, the initial momentum is 3 times 30 plus 5 times negative 18, which better be 0. And so my final momentum is 0 meters per second. In other words, they're going to hit and stop in this reference frame. Works beautifully doing it this way. We didn't have to worry about any relative velocities here. We do have a convenience here of this 30 came from the initial velocity, V3 initial, minus this velocity right here, which I've been calling U. And this was the initial velocity of the 5 minus the velocity of the prime frame. So that would be V prime 5 initial, and this is V3 prime initial. Questions to here? I'm going to use this as a jumping point for throwing relativity into it. All right, let's make it relativistic now. Instead of 48 meters per second, 0.48 is beta 3 initial. Or, I guess if we went in terms of velocity, velocity of 3 initial would be, let's state this explicitly, positive to the right, is 0.48 times the speed of light. So all I'm really doing here is changing some units. So this becomes 1.44 times the speed of light is my initial momentum, plus 0. And we end up with 0.18 times the speed of light. Now, one big difference is that in the first problem I did, I just said 3 kilograms. That was the rest mass because it's traveling slowly enough. Here, I didn't specify it, but this 3 kilogram here would actually be a relativistic mass. But I'm not worried about that at the moment. We can pretend it's a rest mass because we're going to end up with a mismatch. Because when I shift to this new reference frame here, so this is now 0.8 C, I know the 5 kilogram mass is going to be coming at me at 0.18 C, and I'll derive that in just a moment. But the 3 kilogram mass, we have to use some relativity here. I know that the initial velocity in the prime frame would be the initial velocity in the unprimed frame minus, it's all left and right, minus u divided by 1 minus v3iu over c squared. So relativistic velocity addition. Once I have the Galilean one, which I did right there, I know the sign in the denominator is the same as right there, and the two velocities I'm multiplying are these two right here. So this becomes 0.48 times the speed of light minus 0.18 times the speed of light divided by 1 minus 0.48 times 0.18 c over c squared. And again, I'm going to attempt to write that neatly. 0.48 c times 0.18 c over c squared. And what do we get? I know it's 0.3 C on top and on the bottom. Now remember that this comes from the Lorentz transformations that we have in the upper left over there. Lorentz transformations comes from the idea of time dilation, the fact that speed of light's the same in all reference frames. So this shifting of the velocity, change of the velocity from one reference frame to the other has nothing to do with whether there's about to be a collision or not.
For the bottom, I had 0.9136.
And so what is the initial velocity of the 3 kilogram mass?
0.32 AC.
So now, if I look at the momentums, my total initial momentum, I get 3 times 0.328 C plus 5 times negative 0.18 C. What do I get?
Negative 89.016.
Negative 89.0136.
16.
I feel like something got lost in that.
0.18. Never mind.
Yep.
I put 18 instead of 0.18.
Ah, that would do it, okay.
We got 0.084.
Yeah, me too.
0.084.
Yep.
C.
There we go. So, my total initial momentum in the new frame, it's obviously not a zero momentum frame, at least based on the way we've done this. After the collision, they're going this fast right here. And so, let's crank through that. So let's do a shift of this one also with that. So we end up with, let's see, the numerator. So we're just subtracting 0.18. So P final would be the 8 kilograms times my velocity shift there, which is 0.18 C, minus how fast it's going, 0.18 C, divided by 1 minus 0.18 C times 0.18 C over C squared, and that whole thing is 0. So if going from, when bringing into relativity, if all we do is shift velocities, we have momentum conserved over on the left, we don't have momentum conserved over here on the right. And this is troublesome. Physicists don't like conservation rules to suddenly not be valid anymore. Also, the idea of conservation momentum comes from Newton's third law and the fact that they touch each other for the same amount of time. So there has to be something different between the two, and that's sort of a justification for, well, the thing that we haven't touched is the masses. The mass must be different. And so that's justification for why we think that the mass changes with speed. So now let's actually derive that without hand waving. Questions up to here before we actually derive the relationship between mass and speed. Or for the modern purist, momentum and speed. Now there's basically three derivations of the relationship between mass and the rest mass. I'm going to do a different tack than I did last time. I'm going to go to my S frame, of course, and I have an object that is moving very slowly upwards. And let's stick with our convention of I hat, J hat. And so the velocity of this particle in the S frame, so unprimed right there, initial, is I'm just going to get u sub 0 j hat, where u sub 0 is a whole lot less than the speed of light. Basically, thinking of it as I'm rolling a ball on the table. At this point right here, a force gets applied. So a force gets applied starting here, and the force is in the x direction, or the I hat direction. So what's going to happen to if I have a particle moving this way and I start applying a force that direction, what's going to happen to the particle?
I mean, it's going to continue to go up, but it's going to go to the right as well.
Yeah. Because I'm not changing anything in the vertical direction here, so the only thing that's changing is the horizontal, and so it'll start out and eventually be heading in that direction. And this is sort of where I'm ending the problem right there, or ending, that's when the force ends. And the particle is traveling in this direction, so this is my V final. And I'm just going to say that the horizontal component is V and the vertical component is U. So V final is V I hat plus U j hat. Not drawing the scale necessarily. And also assume that the force is applied enough so that V is much greater than U. So it's almost dominated by this x direction. What's the relationship between force and momentum?
Force times time is momentum,
Okay.
or momentum over time.
Or the calculus version, dp dt. Not just momentum over time, it's the change in momentum. That's the critical piece. All right. Since the force was in the x direction, the only change in momentum is in the x direction, or I hat direction. So f of x would be dpx dt. And f of y is 0, which is dpy dt. In essence, my momentum in the vertical direction or in the j direction doesn't change. So if my mass here is m sub naught, again, we're making some claim that there's a connection between the mass and speed, so the m0 here is close enough to the rest mass because u sub naught really slow, and the mass here is m. So we have this relationship that m sub 0, u sub 0 is equal to m u. Just looking at the vertical component of it. Questions to hear? Now, of course, the S prime frame. S prime, not 1. And I want the S prime frame to be traveling at some speed v. So in essence, because the S prime frame is going to be traveling at the exact same speed as the horizontal component here, it's going to, the particle at the end of this force is going to look like it's going straight up. But since it's starting out really slowly, it's going to start looking like it's heading towards the S prime frame. In essence, if we looked at it from the S prime frame point of view, the particle looks like it's doing this, where that's vertical at the end. And so my initial velocity in the prime frame is equal to v I hat, v prime I hat plus u naught prime j hat. Oh, negative there. And at this point right here, my v final in the prime frame is equal to, well, the I component's gone, and it's now u prime j. It's still u naught prime at the bottom because it's the shift of that initial velocity there. It's not, u naught doesn't have to be close to 0 in this particular, well, sorry, u naught is close to 0 here. U prime naught does not necessarily have to be close to 0. And again, the exact same reasoning, because at this point, there's a force being applied this way, which is slowing it down in this direction, which means the horizontal piece gets closer and closer to 0, and that's when we stop. So in the vertical direction, my momentum is the same. So down here, it's m times u naught prime, and up there, m sub naught times u prime. So we have two different relationships here, and let's put them together. So I got m naught, u naught, and then mu, and then I'm going to divide by m u naught prime and m naught u prime. So just basically taking that equation over there and dividing by this equation. I'm going to get the m's together, so I got m naught squared and over m squared, bringing that up and this down. Bringing the u's over, that's going to be, well, let's see, bringing u naught prime up there. And on the bottom, I got u prime, u, and then bringing u naught prime up. Oh, I did that one already. Bringing U stays up there, bringing U naught down. I did that in the ass backward way. So I got U prime, U naught, U and U naught prime. Okay. I'm gonna change the order around here, which is what I was trying to do in one step, and apparently couldn't walk and chew gum at the same time. Basically, I want the U naughts together and the non-knotted together. These are the velocities that are perpendicular to the motion of the prime frame. This gets in play. Doing the beginning there, I know that U naught prime is equal to U naught divided by gamma 1 minus U Vx. Vx is the speed in the x direction at that time, which is, yeah. Initially, Vx is 0 over c squared. So it's U naught over gamma. Looking at the other one, U prime is equal to, again, plugging that equation, U over gamma 1 minus U times Vx. That's how fast, that's what the velocity is in the x direction at the end. So that's V over c squared. Feel like I lost something there. Dang it. Felt like I was on a roll. Yeah, well, that was good.